A very good morning to all of you. I am Dr. Naveen Kumar Devangan, Professor in the Department of Electronics and Telecommunication Engineering, Bhilai Institute of Technology, Durg. It is a great pleasure to be here today with you all and talk about the exciting world of biomedical instrumentation and sensors in the fascinating realm of magnetic resonance imaging. First of all, we will start with introduction of MRI. Here we will see MRI as a form of scan, non-invasive and painless procedure to provide precise images of the body's internal organs and tissues. A thorough cross-sectional image of interior organs and structures is produced by an MRI scan using a powerful magnet, radio waves and a computer. Then we will see why do we need MRI scan. Many body parts can be examined using an MRI scan. It may yield more accurate data than a CT scan for certain body parts and tissue types. Here we will see the list of organs and tissues where MRI images can be constructed to detect healthy and diseased tissues of the section of the interest. Then we will see the basis of NMR. Here we see principle of image construction using MRI scan. Then a comparison of MRI scan will be made with CT scan. Then I will talk about basic MRI components and explain block diagram of MRI scan system. We will also talk about free induction decay FID and Fourier transform of free induction decay signal, which is one of the important steps of image reconstruction in MRI imaging system. And finally, we will see classification of various NMR imaging methods. Now we are going to see the brief introduction of MRI imaging system. Magnetic resonance imaging, in short MRI, or nuclear magnetic resonance, in short NMR, has powerful imaging technique in the medical field because of its high resolution capability and potential for chemical specific imaging. Although similar to the X-ray, computerized tomography CT, it uses magnetic fields and radio frequency signals to obtain anatomical information about the human body as cross-sectional images in any desired direction and can easily discriminate between healthy and diseased tissues. MRI images are essentially a map of the distribution density of hydrogen nuclei and parameters reflecting their motion in cellular water and lipids. The total avoidance of ionization radiation, its lack of known hazards, and the penetration of bone and air without attenuation make it a particularly attractive non-invasive imaging technique. CT provides details about the bone and tissue structure of an organ, whereas NMR highlights the liquid-like areas on those organs and can also be used to detect flowing liquids like blood. A conventional X-ray scanner can produce an image only at right angles to the axis of the body, whereas the NMR scanner can produce any desired cross section, which offers a distinct advantage to and is a big boon for the radiologist. MRI systems provide highly detailed images of tissue in the body. The systems detect and process the signals generated when hydrogen atoms, which are abundant in tissue, are placed in a strong magnetic field and excited by a resonant magnetic excitation pulse. Hydrogen atoms have an inherent magnetic moment as a result of their nuclear spin. When placed in a strong magnetic field, the magnetic moments of this hydrogen nuclei tend to align. The nuclei have as a resonant or Larmor frequency determined by their localized magnetic field strength, just as string has a resonant frequency determined by the tension on it. For hydrogen nuclei in a typical 1.5 Tesla MRI field, the resonant frequency is approximately 64 megahertz. Proper stimulation by a resonant magnetic field or RF field at the resonant frequency of the hydrogen nuclei can force the magnetic moments of the nuclei to partially or completely tip into a plane perpendicular to the applied field. When the applied RF excitation field is removed, the magnetic moments of the nuclei precede in the static field as they realign. This realignment generates an RF signal at a resonant frequency determined by the magnitude of the applied field. This signal is detected, processed, and used to generate an image for display and record. Strong magnetic fields and radio waves are used in magnetic resonance imaging, and it is a form of scan to provide precise images of the body's organs and tissues. A huge tube with a strong magnet is an MRI scanner. During the scan, subject lie within this tube. MRI scans are used by medical specialists to identify a range of disorders including tumors and torn ligaments. The brain and spinal cord can be examined with MRIs. MRI scanning is a non-invasive and painless procedure. A thorough cross-sectional image of interior organs and structure is produced by an MRI scan using a powerful magnet, radio waves, and a computer. A typical MRI scan machine is shown in figure 1. You can see it as a huge machine. We can observe in this figure that a typical machine has a patient bed, a magnet to produce strong magnetic field, gradient and RF coils, and scanner system. Now I am going to explain why do we need an MRI scan. Many body parts can be examined using an MRI scan. It may yield more accurate data than a CT scan for certain body parts and tissue types. An MRI can be utilized to detect abnormalities such as cysts, tumors, and others throughout the body. Women at high risk of breast cancer should get screened for the disease to find out how big it is and whether it has spread, that is to find out the stage of cancer. Measure blood flow to check how well treatment is working. Joint injuries or anomalies such as those to the knee and back. MRI scans are particularly good for anomalies of the brain and spinal cord. They are also good for brain tumors, primary bone tumors, soft tissue sarcomas, tumors affecting the spinal cord, tumors in the pelvic organs like prostate, bladder, uterus, and ovaries. Useful for certain types of heart problems, also useful for disease of the liver and other abdominal organs. MRI also suitable for suspected uterine anomalies in women undergoing evaluation for infertility. Before the scan, you might receive an injection of a particular dye contrast media. This is to help make the picture clearer. Now we will see basis of NMR. Molecules of water make up the body. These molecules, hydrogen nuclei, have magnetic dipole moments and angular momentum. The magnetic moments of the nuclei are haphazardly or randomly oriented and have no net magnetization in the body tissues, so magnetization M is equal to 0. You can see in figure 2 random alignment of the magnetic moments resulting in 0 net magnetization in absence of field when B naught is equal to 0. Some of the randomly oriented nuclei experience an external magnetic torque when a material is placed in a magnetic field B naught. This external magnetic torque tends to align the individual parallel or anti-parallel magnetic moments to the direction of an applied magnetic field. The tissue has a net magnetic moment m naught as a result of an excess of nuclei that are parallel to the magnetic field. In figure 3, we can see that how in applied field nuclear magnetic moments align themselves, giving rise to a net magnetic moment in the direction of magnetic field B naught. When a hydrogen proton is placed in magnetic field, it tries to align itself with the magnetic field. This causes the magnetic moment to precess or wobble about the applied magnetic field with a resonant angular frequency omega naught called Larmor frequency. W naught is equal to gamma B naught, where gamma is the magneto-gyric ratio. In figure 4, we can see precession of the nucleus about an applied field with a resonant angular frequency omega naught. The perturbation of this alignment of the nuclear spins is done by a weak oscillating magnetic field, usually referred to as a radio frequency RF pulse. The oscillation frequency required for significant perturbation is dependent upon the static magnetic field B naught and the nuclei of observation. Nuclei respond by producing an electromagnetic signal with a frequency characteristic of the magnetic field at the nucleus. The strength of the static magnetic field, the chemical environment and the magnetic properties of the implicated isotope all play a role in this process, which occurs close to resonance when the oscillation frequency applied equals the intrinsic frequency of the nuclei. Commercially available MRI scanner for routine clinical use perform from 0.2 to 3 Tesla, while research facilities currently perform human imaging in the fields up to 11.7 Tesla. The frequency is similar to very high frequency and ultra high frequency television broadcasts in between 60 MHz to 1000 MHz. The two magnetic fields are usually chosen to be perpendicular to each other, as this maximizes the NMR signal strength. The scanner itself typically resembles a large tube with a table in the middle, allowing the patient to slide in. Now we are going to see the comparison of MRI and CT scan system. Unlike CT scans and X-rays, MRI scans do not utilize potentially dangerous ionizing radiation. An MRI scan employs radio waves and powerful magnetic fields, whereas a CT scan uses X-ray. Although MRI scans give more detailed images, CT scans are more widely used and less expensive. In an NMR imaging system, cross-sectional images of any orientations are achievable. NMR imaging, in contrast to CT, does not require gantries, moving parts, or specialized crystal detectors. Electrically controlled magnetic fields are superimposed as the system scans. As a result, scanning in any predetermined orientation is conceivable. With the new methods being developed, NMR now allows for simultaneous imaging of complete three-dimensional volumes as opposed to the slice by slice method used by traditional imaging technologies. Now we will see basic MRI components and block diagram. Basically, MRI has a magnet, an RF transmitter, gradient system, detection system, and computerized imaging system. We can see all basic components of MRI in figure 1 and in figure 5. A magnet which creates a powerful, stable and uniform magnetic field B naught. An RF transmitter which provides the simple radio frequency magnetic field. A gradient system which generates regulated, especially non-uniform time varying fields along three directions with x, y and z gradient coils. A detection system which yields the output signal, and a computerized imaging system that reconstructs and displays the images. Figure 6 illustrates the inner working of MRI system. You can see within the metallic cocoon of an MRI scanner, the patient is surrounded by 4 electromagnetic coils and the components of a transceiver. Patient wears loose clothing, must empty packets of metallic objects that could prove harmful if moved by magnetic force. Main coils surround patient with uniform magnetic field. X coil creates varying magnetic field from left to right across scanning tube. Y coil creates varying magnetic field from top to bottom across scanning tubes, while Z coil creates varying magnetic field from head to toe across scanning tube. Thus, X, Y and Z gradient coil allow 3D scanning of the tissues of interest. Transceiver sends radio signal to protons and receives signals from them. Scanner uses electromagnets and radio signals to produce cross-sectional images. The image sequencing in the system is provided by a computer. Software is used to control a variety of operations including gates and envelopes for NMR pulses, blanking for preamplifiers and RF power amplifiers, and voltage waveforms for gradient magnetic fields. Various data processing functions such as Fourier transformation, picture reconstruction, data filtering, image presentation and storage are also carried out by the computer. As a result, the computer needs to be fast enough and have enough memory to handle processing large image arrays and data. Table 1 shows the NMR parameters of nuclei of interest in medicine. Not only hydrogen isotopes but also isotopes of carbon and nitrogen can be used to obtain MRI images. Nuclei hydrogen 1H offers nuclear spin of half value and gamma upon 2 pi value of 4.26 MHz per kg, where gamma is magnetogyric ratio. Nuclei carbon 13C is having nuclear spin of half value and gamma upon 2 pi value of 1.07 MHz per kg. Nuclei nitrogen 15N offers nuclear spin of 1 value and gamma upon 2 pi value of 0.31 MHz per kg. The ratio of excited particle to particle at rest and other properties of particular nuclei determines the NMR sensitivity. Table 2 gives NMR frequencies and other characteristics of some of the common biological isotopes. Element hydrogen has 10% of body weight, isotope is 1H and has NMR frequency in megahertz per Tesla is equal to 42.57. Element carbon has 18% of body weight, isotope is 13C and has NMR frequency in megahertz per Tesla is equal to 10.70. Element nitrogen has 3.4% of body weight, isotope is 14N and has NMR frequency in megahertz per Tesla is equal to 3.08. Now coming to free induction decay, that is FID. In NMR at room temperature there are more protons in a low energy state than in a high energy state. The excited protons tend to return or relax to its low energy state with a spontaneous decay and re-emissions of energy at a later time t in the form of radio wave photons. This decay is exponential in nature and produces a free induction decay signal which you can see in the figure 7, and this FID is the fundamental form of the nuclear signal obtainable from an NMR system. If in a static field RF waves of the right frequency are passed through the sample of interest or tissue, some of the parallel protons will absorb energy and be stimulated or excited to a higher energy in the anti-parallel direction. Sometime later, the radio frequency absorbed will be emitted as electromagnetic energy of the same frequency as the RF source. The amount of energy required to flip protons from the parallel to the anti-parallel orientation is directly related to the magnetic field strength. Stronger fields require more energy or higher frequency radiation. The tissue's net magnetization would shift somewhat away from the z-axis. If it were now exposed to another magnetic field such as one created by a bar magnet placed along the y-axis through an angle alpha, you can see in figure 8. We can get the same result if we apply an RF pulse at the resonant frequency of the protons in the tissue. The angle of rotation depends on the amplitude but primarily on the length of the applied RF pulse. So, alpha rotation is equal to kT, where T is pulse length and K is constant. In figure 8a, we can see that the magnetic moment is flipped from its equilibrium by the application of another magnetic field direction at a high angular frequency which is proportional to the field strength. And in figure 8b, we can see that it then processes about the external field direction at a high angular frequency which is proportional to the field strength. An RF pulse of sufficient duration and power to rotate m naught through 90 degree is referred to as 90 degree RF pulse. Magnetization can even be completely inverted and the corresponding pulse is called 180 degree RF pulse. When RF pulse is turned off, the net tissue magnetization begins to swing back towards the z axis along direction of B naught, inducing an NMR signal in the receiver coil placed perpendicular to the moving magnetic vector. The amplitude A of the signal received by the coil is proportional to the magnitude of the component of magnetization in the xy plane, that we write it as mxy, as well as various geometric factors. The two relaxation methods listed below are seen to be connected to nuclear spins that are excited. A relaxation time T1 referred to as spin lattice relaxation process. It also determines how long it takes for disturbed nuclei to realign with the host material's current lattice structure. This is also called longitudinal relaxation. Now B, relaxation time T2, it is referred as spin relaxation. It is the time required for the perturbed in phase spins to dephase with respect to each other. It is also called transverse relaxation process. Transverse relaxation is faster than longitudinal relaxation time constant. If T1 is sufficiently short, the resultant signal amplitude with both decay process contributing would be amplitude A is equal to A naught e to the power minus T upon T1 into e to the power minus T upon T2. Relaxation process play a crucial role in NMR. Variations in relaxation periods between various biological tissue types serve as the primary contrast mechanism for anatomical discrimination in imaging. The discrepancies in relaxation times from the normal values can be larger than 100% in a sick state, offering a potent mechanism for the pathology's identification. NMR imaging is a distinctive, adaptable and potent method of medical imaging due to the imaging capabilities of these two crucial parameters T1 and T2 as well as the proton densities of the objects. We are interested in identifying the frequencies that are present in the NMR spectrum and figuring out how intense each frequency is in NMR imaging system. It is necessary to convert the time domain FID signal to a frequency domain function. To do this, we employ Fourier transform to identify the NMR frequencies and intensities that are present in the time response of a nuclear spin system that has been exposed to an RF pulse. The fact that medical NMR images can be most easily generated from the resonance of hydrogen nuclei is fortunate because the human body is 75% water, each molecule of which has 2 hydrogen nuclei. Moreover, the distribution of water along with that of various other small hydrogen rich molecules, for example lipid, is known to be altered by many disease states. These are of the order of 10 to the power 22 hydrogen nuclei per gram of tissue to provide a respectable population base from which the feeble NMR signal can be received. Other nuclei such as phosphorus 31p, carbon 13c, fluorine 19f, sodium 23Na, nitrogen 14N and oxygen 17O are orders of magnitude less abundant in the body and have weaker magnetic moments. There are two methods of measuring the NMR signal. One is the continuous wave method, in which spin response are recorded by sweeping the magnetic field strength or exciting frequency near the resonant point by continuous radiation of electromagnetic waves for excitation. The other is the pulse method, in which the spin response is recorded after impressing radio waves that are pulse modulated and have frequencies near the resonant frequency. The spectrum data of the frequency domain is applied on the former and the free induction decay signal of the time domain is applied in the later. The pulse method has several advantages such as obtaining the spectrum of wide frequency domain at one time and and of the possibility of measuring parameters T1 and T2 directly, which describe the time response of the spin system. Virtually all NMR imaging methods use the pulse method. Now we are going to see image reconstruction techniques which are generally used to create image of the body or tissues of interest. We can see that first, the tissue's proton density can be used to create an NMR image. Second, the T1 relaxation time distribution of the same section can be represented by another image. Third, it is possible to produce a third image of the section that represents the T2 relaxation time distribution. Fourth, yet another NMRI image sensitive to flow can be reconstructed. The majority of NMR images nowadays are a combination of these four parameters which are combined to best reflect the anatomy or pathology of the organs or area of interest, despite the fact that some NMR imaging equipment is capable of creating calculated T1 and T2 images. Now we are going to see classification of various NMR imaging methods. First, sequential point method. Second, sequential line method. Third, sequential plane measurement. Fourth, simultaneous measurement. While creating image, the total imaging value is divided into a grid matrix of rectangular cells called voxels along the three spatial coordinates. We will assume z axis coincident with the axis of the cylinder of the MRI machine. In the sequential point method, the sample volume is divided into Nx, Ny and Nz volume elements along the three respective Cartesian axes as shown in the figure 10. Then Nx, Ny, Nz independently measured values of the NMR signal are required to completely reconstruct the image within this volume as shown in the figure 10. It is observed that a continuous resonance signal could be obtained by subjecting a sample to a continuous string of intense RF pulses. In the sequential line method, volume elements along an entire selected line, for example, in the y direction, are simultaneously observed, reducing the total number of the experiments required for the complete image to n is equal to nx nz. Figure 11 illustrates the sequential line method. The method utilizes two orthogonal time dependent magnetic field gradients, an SSFP pulse sequence and signal averaging to spatially localize the NMR receiver sensitivity to a line as in the sensitive point method. The distribution of spins along the line is determined by applying a third linear magnetic field gradient in the direction of the line that is time dependent. The NMR frequency would thus directly correspond to the spin density distribution along the line and can be obtained by the Fourier transformation of the time average FID signal. The sequential plane method permits the simultaneous observation of an entire imaging plane, and for that matter, total number of experiments required for the complete image n is equal to nz. The simultaneous observation and resolution of entire plane of points requires a dynamic range capable of nx ny pixels, which places stringent demands on instrumentation and bandwidth. Image reconstruction using this method is shown in figure 12. In simultaneous measurement method, the gradient is reoriented in all 3 dimensions, and 3-dimensional image is displayed as a series of planes in any desired orientation as shown in figure 13. Now, I am going to display some sample MRI images of different persons. Figure 14 is the MRI image of the brain for normal case, and in which different parts of the brain are mentioned. MRI obtained from the patient is compared with normal to detect any anomalies or abnormality. Figure 15 is the MRI image of head taken in 3 different planes. I have shown 2 MRI images of the brain in figure 16. You can observe here that the left side image of the MRI shows normal tissue in a particular section of interest, but the right side shows abnormal tissue in that section, showing some sort of brain related disease, tumor or cancerous cell. These are the important topics in MRI imaging, and I have covered one by one all the topics. I have explained why MRI is needed, what is the basis of NMR images. I have also compared MRI with CT. We have seen basic MRI components and block diagram of MRI system. We have also seen what is pre-induction decay. Then we also saw Fourier transform of FID, and finally I covered image reconstruction techniques. With this, I complete my today's lecture on MRI imaging. If you need any further information or clarification, feel free to contact me through my mail naveen.devangan@bitdurg.ac.in. In my next lecture, I will be available with another interesting topic of biomedical instrumentation and sensors. Till then, goodbye. Thank you all.